Hello, my name is Carlos Serrano, and I will be presenting Group Seven's project, which was the development of a scale vehicle with semi-autonomous control. And so our challenge was to develop a semi-automatic two-scale vehicle, which aligns with the Sustainable Development Goal number 9, showcasing how automation has a role in the efficiency and sustainability of processes. It is designed for agricultural applications and features manual and automatic modes with STM32 microcontroller controlling and obstacle avoidance and remote communication through um, Bluetooth modules. This innovation highlights the engineering's potential for a more sustainable and resilient future. So our challenge requirements include how our vehicle must have remote communication system for data transfer and control. We developed a system through Bluetooth signaling. At least two control loops must be implemented, speed control and direction control, which we also implemented distance control. And our vehicle must operate in manual and automatic mode. For manual mode, each control of the vehicle must respond to a change of reference. And on automatic mode, the vehicle must follow a pre-programmed trajectory completely autonomous. The robot must track the following trajectory as close as possible, move X meters heading north, X meters heading east, X meters heading south, and X meters heading west, where X meters was a distance between 5 and 20 meters. So our robot must stop for 10 seconds on each waypoint, and the robot must end at the same place where it started. In manual or automatic mode, the vehicle must be able to do obstacle avoidance, and that is why we utilize an ultrasonic sensor. So our proposal includes the following components. We have an STM32 Blue Pill as our microcontroller, specifically the STM32F108 103C8. We used dual H bridge, specifically the L298N module. We use FC03 sensors as our encoders for feedback and the closed loop system. We utilized four DC motors for each wheel of the vehicle and a gyroscope, specifically the MPU 6050 module. For communication purposes, we utilized HC05 Bluetooth module and the HCSO for ultrasonic sensor. And finally, we use the SSD 1306 OLED display for variable displaying. Here we can see the final schematic of our project with all given modules and also energy fitting. So, stated in the requirements of our program, of our challenge, we needed to program two sections or two modes of operation, which were automatic and manual. That is why we utilized a remote controlling system through Bluetooth. We utilized the serial Bluetooth terminal application in order to develop a system in which we send specific uh, instructions to our program or to our microcontroller, and that our vehicle would respond to it. So for manual operation, you can see that we have buttons for forward and backward movement, stopping, increasing and decreasing speed, and left and right turning. We also, for automatic mode, we had this different distances set for our car to travel. You can see that we have 2 meters and 3 meters. And if the automatic mode button was pressed, then our car would start the automatic sequence that was stated before. So our challenge required us to implement at least two controllers. So we utilized first velocity control. This controller was the first one that was developed due to the fact that it was essential for correct functioning of the other two controllers. We start by initializing our STM32 Blue Pill. We check the encoder for initial feedback. This encoder, of course, is what makes our system closed loop. We check if the feedback signal is present. If it is, then we calculate an error between the desired speed and an actual speed. We make a set point for the speed that we desired, and we adjust the PWM signal sent to the H bridge. This modulates the frequency to the DC motors, and the DC motors adjust based on the frequency modulation. This basically represents our feedback loop, which then returns to the encoder for new speed feedback and new instructions. If the desired speed is reached, then we maintain the current settings, and that basically represents the velocity control. On the other hand, we have the direction control, which is based around the MPU 6050 gyroscope. We initialize it and check if all of its information and data is correct. If it is, then we read the gyroscope to gather raw data and filter the data that we need. As we know, the gyroscope could have a lot of noise in the data that it is giving. So we start an internal timer to create internal interruptions every 100 milliseconds given our system's internal clock, prescaler, and ARR configurations, we have an output frequency of 10 hertz, and that gives us a capture period of 100 milliseconds. We filter this data in every interruption, applying an error margin to have more control. We calculate the error between the degree and the angle tolerance. If the angle tolerance is between the margin of error, then we calculate PWM correction proportional to error for each of the sides of our vehicle. And we apply the corrected PWM to the left and right motors to realign the vehicle. So that represents direction control, and we lead to the final controller, which is for distance. We start by initializing our STM32, and we input the target distance and the total time that our car has to reach that set distance. We configure a function that we created and calculate the nominal speed. If the nominal speed is less, well, it's not real for the parameters that we enter, then we get a command that our movement is not possible. And if it is, then we speed set to nominal velocity. We therefore calculate constant velocity time. Our distance control performs movement in trapezoidal form. We're having an acceleration time, a nominal speed time, and a deceleration time. We get the total time with each of the times for each given phase, and we calculate the distance, which is the area under the curve. And we start a timer for the interruptions and therefore perform the calculations and give the given PWM signal to our motors to move in each phase and finalize in the distance that we stated. We finalize movement by setting the PWM to 0 and putting the motors in reset. So we carried out the following tests for our project. We had a distance control test, a path control test, a velocity control, and steering control test. So right now you will be able to see how those tests turned out. So the results that we achieved, we start with the showcase of manual mode operation. So basically that highlights the manual mode of operation. You can see how our system responds to Bluetooth communication signaling and gives different directions to our car. Then we have automatic operation. You will see how our system follows the given sequence, which was somewhat of a square. This square was not perfect due to different factors as differences in hardware and some considerations that were not taken. But in the end, it is at least three-fourths of the complete sequence. So that is how our automatic mode of operation looks. And then we have the following test, speed control test. As you can see, with the PID controller that was developed, we give a set point to our system, and the PID controller gives an output delta PWM, which would be added or subtracted from the PWM signal in order to make our error the least and follow the given set point. And finally, we have the path control test. So basically, that was the path control test, checking that our gyroscope correctly uh, communicated with with the velocity controller to give different velocities to each of the sides, so that our vehicle returned to its set path. And basically, that is all of the project. That is our results. And overall, it was a project that really challenged us to understand how controlling systems work, how communication systems work, and how autonomous applications are created. This is our bibliography with each of the modules data sheets. And that is basically it. Thank you very much.